Hello. Okay. So, yeah, I just thought I would, you know, start learning different things. So I thought maybe modeling, mathematically modeling financial assets and derivatives could, you know, help me in the future. And also I started this like around 4 months ago. So I thought maybe, yeah, let's just go down in this part as well. So I was thinking, to continue this. So, So before I started, uh, I just found another book I want to read. It's more mathematical, I assume, compared to this book I currently am showing you. So this is this one, and yeah, maybe we would do both of these books, parallelly. The book I found more mathematical was this one. So I was thinking maybe we will go with this in future, but for today I have read this random walk part from this book. So I'll just you know explain the part I have read that would be from you know this one. So this part right here. I'm not this. So 2 point. So yeah, let's just get into it. So what is the random walk? So it's just that hmm, the random walk hypothesis is that the you know gross returns RTs are independent. So yeah, that's what it says right here, where RT is the gross return, which is yeah, uh, yeah, that's what the hypothesis is. And if we assume RT is normal, then this is called normal random variables. So uh, I'll look at that. This is actually that's what we assume because you know yeah, we will see what and the mock is, and then we will see how this comes. Why log appears here. So a random work is like you're at state S naught, and at time 0 to t, uh, this let us say changes from S naught to S1, and the difference here is let us say Z1. Then if we do that for uh, you know longer times, we get something like the status ST would be like then I'm sorry, ZT. This is a random walk, and we try to, assume or find ZT so that we can approximate ST. So this is what a basic random walk is, uh, and we consider that one Z2 to be IIDs. So yeah, so ZI are independent and identically distributed. So yeah, that's what it is about. So why do we take the differences and model them? Because we can model more information in that way, or we can say that this is generally the case where you know uh, the differences are independent. I mean, generally, I mean this is a good assumption. That's what I think. Yes. So if we assume that they are normal, then it is a normal random. And if I have a mean mu and variance sigma, normal or not, okay, then we know this that let us say x is sigma xi, then expectation of x is you know sigma xi, and variance of x is mm, I don't remember the formula exactly. It should be something like e of x square plus 2 into covariance of xi comma xj, something like this. I think so. So now, so for sigma zi, this becomes n mu, and variance becomes, well, the standard deviation becomes n sigma square. So z, which is sigma zi, is now normal, right? If you consider it as normal. So we get something like this. Yep. So this, so st would be something like s naught plus z, which is not plus something like the square. So obviously the st would be something like s naught plus t. That is mean of this line, which is this mean, and this is the variance about times. Actually, it's like this. So the mu here is called drift because that's where the value is moving. The average is going to at after some time t at that rate, right? So and sigma is called volatility, whatever the spelling is, uh, because how it changes. I mean, yeah, if you know the distribution variance is generally called volatility. So yeah, so how this relates to our you know returns here is that we know log of the returns are something like this, right? So that is exactly what you want, right? So if we can, so my PT would be as PT is P naught AXP. Alright, if you have to log on both sides, log PT would be something like this. I'm sorry, did I make a mistake? I think I did. Yeah, it's something like that. Wait, what? No, that's not right. Yeah, I'm sorry. Okay, so the thing is, I was confusing you with gross returns and log returns. So RT is log returns. So you don't have the log there. Okay, it's like yeah, because it's the log returns. So you get something like this. So now it's very similar to similar to random walks right here, right here. So that's what we do. Now we got something like this. Yeah, that's how we model it. Now if we assume Okay, so if you use logarithm in random walk, it becomes geometric random walk or an exponential random walk. And if we assume, you know, RIR square, that becomes log normal because we are not exactly, modeling PT directly. We are modeling log of PT. So log normal. So it's called log normal geometric random walk. Yeah, but are prices generally log normal random walk? No, obviously not, because we are assuming that the returns are normal, which is generally not the case. And it's more like a T distribution. That's what the book says as of now. A T distribution is where you have some degree of freedom, I guess, with some heavy tails. And the other thing is, the second assumption is that the these are independent. So that's certainly not the case because if you see high volatility at the current time, like if you see high volatility at this step, you assume that there's going to be high volatility at least for some time. So if I see like the market is so volatile at let us say t equal to zero, I assume that is generally the case that it's going to be volatile at t equals to one, t equals to or something close. That is called volatility clustering, and that is generally the case. So we can't assume they are, you know, independent. So yeah, and yeah, we will. That's it. From tomorrow, we will look at another book uh, that I think is more mathematical. There's this book. We will start tomorrow at assistant dynamic, or maybe from the introduction. So tomorrow I'm going to read this part and explain to you what I understood. I think. Uh, yeah, that's it. Bye.